Okay, so am I audible?
Yes, sir.
Okay, fine. So, so it's already nine. Yeah, it's already nine. So let's start the class. So I am Mrinmoy Bonik, as you can see my name on the screen. So this is your first class in RSN, right? So all of you have never joined RSN before, right?
Sir, could not hear you. Could you, sir, you're
Okay.
not that audible, sir. I mean, I can't hear you that very well, sir. Could you speak louder, sir?
Is it okay now? Hello.
Yes, sir, yes. Now it is okay.
Okay. So all of you introduce yourself one by one first. So let's start with you, Pritish. What are your hobbies and all? Like, where are you
Sir,
from?
I'm Prithvish. I'm currently studying in the 11th standard. I study in Birla High School. For now, I don't have any hobbies because the pressure is too much.
Okay.
Yes, that is it. That is it.
And where are you from?
I'm from Bada Bazar.
Okay. Okay. Next. So who's next? I can see Niloy Day. Yeah, Niloy Day. Can you please unmute yourself and introduce yourself? Like just a few words.
Uh, Hi, I'm Niloy. I'm taking a job here and I'm preparing for the ISICM exam.
Okay. And where are you from, Niloy?
Oh, I'm from Kolkata.
Okay. Okay. So okay. So next, Koshani. Right. So Koshani, can you
Sir,
unmute yourself? Yeah.
sir, I am Koshani Tambuli from Bagmore, Kastrapada. I am currently studying in class 11 standard from Harnett English Medium School.
Okay. Nice to meet you. So next we have Shona Gupta. Yeah, Shona.
Hello, my name is Shaunak Gupta, and I also study in the 11th standard at Park Street St. Xavier's Collegiate School, and I'm also preparing for the ISI exam. My hobbies are playing chess.
Oh, so you play chess. Nice. Are you a rated player or something? Hello,
No, no, no,
Shona.
not still a rated player. No, no, no.
Okay. So now we have Sujan Sanjay. Right.
Hello, guys. My name is Srujan Sanjay. I'm studying in 11th. I My hobby is reading fiction books, and I'm here to study for the ISICMI entrance.
Yeah, and from you are from which school?
The Purna Learning Center. Also, I'm from Bangalore.
Okay. Okay. Nice. Then there is Shapronia Bishash. Right. So Shapronia,
I'm
am I
Sophia.
pronouncing your name correctly?
Yes, sir.
Okay. So where are you from, Shapronia?
Sir, I'm from Siliguri.
Okay. Which school?
Sir, Delhi Public School.
Okay. So you are in 11th standard, right?
Yes, sir.
Okay. So next we have Adrija, right? Adrija Poddar.
Yes,
Yeah.
sir. Sir, I'm Audrija. I'm from Kolkata. I'm currently in 11th standard in Mahadevi Birla World Academy.
Okay. Nice, nice. Did I leave out any one of you? I don't think so. So you are one, two, three, four, five, six, seven. Yeah, seven of you are present right now. Maybe rest will join in a few moments. So let's start. So yeah, so this is mostly we will talk about some notations and symbols used in proofs or in the context of number theory in this first class. So all of you can see the screen, right?
Yes, sir.
Okay, so this is so all of you recognize this symbol, right? This is the also known as the blackboard capital N. This is used to represent the set of numbers which are natural. So the set of natural numbers. Natural numbers. Next we have the Z, capital Z. This is used to represent the set of integers. So it's basically the natural numbers along with the negative natural numbers. So these are not actually negative numbers. So you can say natural numbers. So you can say Z plus is equal to n. So Z plus can also be alternatively used for the set of natural numbers. And then we have the set Q. This is the set of rationals. And finally we have the set R, set of real numbers. Uh, some of you also might have heard about this set. Actually, it's much easier to write this as this. This is the set of complex numbers. Here we are only gonna deal with this set, the set of natural numbers, and sometimes we will like to extend our theories and postulates to the set of integers and the set of rational numbers. We will mostly not go into complex numbers and real numbers in this part, in this section. Okay, so what are natural numbers? Like, why are they so special? So it's so you can actually so those are the numbers that humans were first to come upon. Like before we even started all this mathematics and arithmetic, we were able to count things. So counting is the key process. Is the key process that revolutionized the what do you mean yeah like the way people kept their memories and the data in the ancient world. They were able to count their cows, their coins, and their houses and everything. How do they count? So you consider anything, like even if you have nothing, so nothing can be like represented mathematically with this set. This is called a null set. This takes its inspiration from a Danish letter which I don't exactly remember. So this is not this phi, which is sometimes you might have seen in trigonometry used as substituents for angles. This is phi. This is an entirely different symbol than this. This is called null set, and this is phi. Similarly, you might also get confused between this and this. So these are different. This is the this stands for infinity, and this is the sign for proportionality. Okay, so yeah, so moving on to counting. With this null set, you can actually generate all the natural numbers. How? You can associate this null set with the natural number, not the natural number, we say it's the whole numbers. So there is another set called the whole numbers, which we don't represent with any letters. Sometimes it gets represented with the letter W, but it's very uncommon. So mostly we are happy using this natural number union 0. So that's the set of whole numbers. So the null set can, you can associate null set with the symbol 0. Then we can associate 1, or this is just the Hindu Arabic number system. But you can use any number system. We will come to number systems later. So, this set, which is a set containing a null set, we can associate 1 with this set, and then we can like continue doing like this, and we can make a set out of 2 elements. The first one is a null set, and the second one is a set containing null set. So we can associate 2 with this set. Then next we can.
Sir, question. Yes, sir. So could you explain that part, sir? I mean, how can one be associated with a null set? A null set does not have any elements in it.
Yeah, this is not a null set. This is a set containing a null set. So you can consider null set as an element. It doesn't have anything, but when you enclose.
So one is the number of elements in that set.
Yeah, so the cardinality of this set containing a null set is 1, while the cardinality of null set is actually 0. So, yeah.
Okay, sir.
Yeah, so when I'm
Sir,
saying.
Then why in the second one there is a set inside a set? That can be null set only.
You mean
Sir,
this one? Okay, this one.
No, sir, next.
Yeah, so I have a null set, right? And I can treat it as a set, or I can treat it as an object or anything. Like, what is a set? It is just a collection of things, right? So I can put anything in there, even nothing also. I can put empty set into a set and call it a set containing one element. So it's not empty because it has a set which doesn't have anything. So that's why we have constructed a set. Yeah, and when I'm saying we can associate 1 with this set, when I can associate 2 with this set, this associate, I'm actually informally referring to that mapping from the set of natural numbers to this set, to the sequence of abstract sets that I'm constructing. Like that operation is that cardinality, right? So what is the cardinality of a set? So it's just frankly the number of elements present in the set. So how do we represent a set? We represent a set
cardinality is the number of elements in the set.
Yeah. So we mostly represent set with these curly braces. So anything inside these curly braces separated by a comma are the elements of the set. It can be like a letter, it can be a number.
Sir, actually my question is why there is why there means wait. So there can be two null set and we can say it as 2. Why it is inside a set only?
Okay, so you mean you want to say this has a cardinality of 2, right?
Yes, sir.
No, actually, in a set, there are only things with multiplicity 1. That is, there is nothing like to duplicate things. Everything is unique in a set. So when you say the set has this null set, it only has one instance of that null set in that set. Nothing like you can't have two null sets in a set because they are the same thing. You can't place two of them in a set. They will be counted as one. So to make
Okay, sir.
two things, we are enclosing one in another set so that it becomes a different thing. Okay, so you got it right.
Yes, sir.
Okay, so yeah, so for 3 we can write simply add another set. We can put this whole thing in here. So yeah, and it starts looking much more messy and complicated from here. So I won't continue like this. Okay. So yeah, so that's how you generate the numbers 1, 2, 3 up to like infinity. So that's the set of natural numbers. So that's how people found the set of natural numbers. Yeah, obviously they didn't use that null set as that entity. They can use anything like coins or like stones or axes, anything. So now we have okay. So next there comes the concept of operators like plus, minus, addition, multiplication, and all that. So mostly there are 4 basic arithmetic operations, right? So plus, minus, multiplication, and division. So how do you execute them, or like how do they appear naturally in this context of natural numbers? So there is these set operations like union, the set difference. Multiplication is a bit complicated. You have to get into group theory for that. So let's not replicate that also. But yeah, so let me introduce a few more set operations. So this is a union. So union. And this symbol stands for set difference. This is a backward slash, remember. We use the forward slash for division and the backward slash for set difference. There are a few other symbols like this triangle used for set symmetric difference. And the intersection used for intersection. We also have, okay, so it's easier to understand the set operation with a Venn diagram. So here we have 2 circles within a rectangular region. So I can call this shaded region a set A. So this orange part is B and the black part is A. And the place where they intersect, this is the, so black and orange, which color they form. Let's say, let me see, color palette. So this is A intersection B. And then the whole, this, what can you say, binocular looking thing, this and this. This is the A union B part. And we have this union of 2 crescent moons. This is the asymmetric difference B part. So necessarily asymmetric difference B is A union B minus A intersection B. So uh, we are removing the intersection from the union to get only those part which is unique to each of the sets. Like only those elements which belong to either A or B but not both. And this is, so what is A union B complement? So there is something called, first let me introduce the complement operation. So something complement, or sometimes also expressed as a bar over the head. So this is complement. It means we are taking a set difference from the universal set. So this rectangle, you can think of it as the U or universal set. That is a set of all, like the whole space of elements that we are sampling from. So this is U. So when you talk about A complement, you are talking about U set difference A, right? So yeah, so this is also equivalent to, yeah, you can express complement as small c in the exponent, or you can draw a bar over the head for the set. So A union B complement can be written as A complement intersection B complement. You see, the union notation gets horizontally flipped into a
So does A bar
intersection.
mean the universal set?
Yeah, this is a universal set.
Okay, sir.
So this small theorem we call the, so this is the De Morgan's law. It just says when we complement, you can say a set formula or a Boolean expression, it's the the unions get converted into intersections, and the intersections get converted into unions. So why does this happen? So let's see with an example. Here we have A and B, and A union B is the whole thing. So what is U minus A union B? So A union B complement is U minus A union B. That is this region. This region, right? So this is our right hand side. So let's see what is on our left hand side. So what is A complement intersection B complement? So A complement is everything like all this shaded region. B complement is this part, right? So you can obviously see they intersect in and form this outer part, which is not inside any of the two circles. So yeah, so that just means these two things are same, right? If you want to be more rigorous, then you have to define some axioms on set operations, which mostly George Boole did, and that's how he founded Boolean algebra. I guess in class 11 in CBSE you will be taught Boolean algebra and all that in your, I guess, in computer science or something. Okay, so so let's not move away from our original discussion on number theory, the set theory. So Yeah, so we have the four basic operations: addition, subtraction, multiplication, and division. We can we have so union is analogous to addition, subtraction is analogous to intersection, difference, set difference, and multiplication and division, we don't have such similar analogies. So okay, so why do we study like number theory? So why number theory? Well, number theory actually helps us to like find the properties or relation between natural numbers. Like when you say 567, we know internally it's 5 times 10 squared plus 6 times 10 plus 7, since we are using the decimal representation, which is the base 10 representation, while in the computer it will be stored something like 567, uh, like you know how to convert a number in decimal to a number in binary. You just keep on dividing it by 2. So first when we divide it by 2, we get 2, 2 2s are 4, we get 16, 2 each are 16, then we have uh, 6 and 1 remainder. Then we have again, we go 1 and then 4, then 1 and again 1 remainder. 7, 0, 1 remainder. We have 35, no remainders. We have 17, 1 remainder. Then we have 8, 1 remainder. Then we have 4, no remainders. 2, no remainders. Finally 1, no remainders. So it's 1 0 0 0 1 1 0 1 1 1. So that's the binary representation for the number 567 in decimal. And how do
So
you,
why does 283 represent 1, sir? Could you explain that?
sorry, can you repeat your question?
So why does yes, sir? Why
Yeah.
does 283 represent 1? I mean, why does 283 represent 1, sir?
No, no, it doesn't represent 1. I'm just writing
Keep the
down the
remainder 1.
remainders over here. Like when you divide 567 by 2, we get, so you can write 567 equal to 283 times 2 plus 1. Right, so this is the division algorithm. Yeah.
Sure.
Yeah, so let me formally introduce you to division algorithm. Division.
So is binary theorem required in number system?
Yeah, it's required in number system, but we are not studying number systems here. We are studying number theory. It's different. Like it's a subpart of number theory. It's number systems.
Okay. Okay, sir.
So what is division algorithm? Uh, division algorithm says when you have two numbers a and b, both naturals, then there exists. Okay, so I didn't introduce you to these symbols. So this here is the symbol for inside, or this is like this means a and b are two numbers which lies inside the set n, which represents natural numbers. And this inverted reflected e, capital E here, represents existence. Exists. Similarly, you have, when you put an exclamation to the side, that means there exists unique. So there exists unique. Similarly, when you invert the this inside symbol, you get another symbol, and this one you call such that. This is pretty rarely used, so I might sometimes use this, but mostly people use h.t instead. Next we have the implies sign, and this is the sign for contradiction. Contradiction.
So could you give an example of there exists unique sir? I could not understand that. There exists.
Okay, so uh, like after this division algorithm, we will soon come over to a next fundamental theorem of arithmetic. So when we will study that fundamental theorem of arithmetic, there we will use this there exists unique symbol, which says like prime factorization, right? So you have a number n, you can factorize it into few prime numbers. So p1 times p2 times p3 dot 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 up to pk. So there are k prime factors of n in total, and each of the prime factors appears, say suppose alpha 1 times, alpha 2 times, alpha 3 times, up to alpha k times. So that is a total prime factorization of n. So here you can say the fundamental theorem of arithmetic says for all natural numbers. Oh yeah, here again we get another new symbol. This is for all. So for all inverted A. Okay, yeah, wait, I will.
Sir,
Keep
n
on.
is a odd number.
No, not necessarily. It can be a prime number, a composite number, an even number, an odd number, anything. Just like it's a natural number, right?
Sir, but multiplication of a prime number can be even number.
No, these are like two is an even, and two is prime, right? You know that. So 2, 3, 5, 7, 13, 11. These are the first few prime numbers. So, and 2 is even here. So if, so what was your question? Can you repeat? It was
Sir,
Roshan,
actually I
right?
told that the
Okay.
product of prime number can be an even number.
Yeah, so 2 times 3 times 5 is 30, which is even number, right?
Yes, sir.
Okay. So we have for all n inside naturals. That is, if we have a number n which is a natural number, and this is true for all natural numbers, so then there exists unique. So then there exists unique set of prime numbers, p1, p2, up to pk, such that these are also naturals first of all, but these are primes, prime numbers. So there exist k prime numbers. K is strictly greater than 0. Since 0 is not a natural number. So for all n inside naturals, there exist unique prime numbers p1, p2 up through pk, and there exist unique exponents alpha 1, alpha 2 up to alpha k. These are exponents, so these are naturals too.
Are
That
these exponents or powers?
Yeah, these are powers actually. Sometimes you call interchangeably use exponents and powers, but actually in power k, this whole thing is called the exponent with exponent of n raised to the power of k. So these are called powers, and this is the base. The whole thing is called exponent. That doesn't matter. So there exist unique alphas such that, yeah. Anyone wants to say something? Okay. Such that this happens. So n can be uniquely expressed as the product of k prime numbers raised to some powers. These alpha is like they are greater. They are non. They are natural numbers, right? So they can't be zero. If you uh, if you allow them to be zero, then we can like express. We can include the whole set of prime numbers in this expression. Like we can go on multiplying prime numbers. If if a prime number doesn't divide n, we can just put zero in its exponent, right? So then it becomes a infinitely long product of prime numbers. By the way, we write product like series product like this by capital Pi. So this is product over. Similarly, we have this. We use sigma, capital sigma for summation. So sum over. Also, we have other notations uh, union over. You can use a large U like this one, and then I want k ai. So this just means a1 union a2 union up till ak. Similarly, we have intersection and what else? What else? Yeah. So this these two notations are pretty wild, but can anyone guess what they represent? Like I runs from 1 through k, ai. This is actually the maximum of all ais. So these two symbols are equivalent, and this stands for minimum. These two are equivalent. Okay, so yeah, so let's first talk about division algorithm. So in division algorithm, just as if we have two numbers, two natural numbers, then there exist uh, two other numbers, q and r, which are naturals too. Not naturals, yeah, right. There's a whole number, so it's union with zero, such that this happens. A equals q times b plus r, where r is strictly less than b. Yeah, you can use there exists unique also, since this r is a unique remainder if you impose this condition that r is less than b. Otherwise, you can allow you can like this is equivalent to a equals to q minus 1 times b plus r plus b. Right, so we can take r plus b as the new r dash and q minus 1 as the new q dash. So we got another set of q dash and r dash. So that's not unique, since we haven't imposed the condition r less than b. If we impose that, we get a unique quotient and remainder. So this r here stands for remainder, and this is the quotient. I'm not writing them down since there's no space, not much space left. Okay, so yeah, right. So that was a division algorithm, and this is the fundamental theorem of arithmetic. Okay, cool. So how do they help us? Like, what can we do with these? So here comes the notion of divisibility. So what's the notion of divisibility? You can say A divides B can be written as this pipeline operator. This is the pipeline operator. On a QWERTY keyboard, you can, I guess, see it on the rightmost part with the backward slash operator. If you press shift and backward slash, you get the pipeline operator on the keyboard. Right. So this here stands for divisibility. This means divides. So this can be alternatively written as A equals QB plus R, where R is 0. And it can also be written as A congruent to 0 mod B. So what does this mean? Right, like this here, this 3 dash looks like the congruent symbol in geometry. This stands for congruence, and this is modulo operator. You can say it's operator. So basically, we have like different kinds of like groups. So what are groups? I'm not getting into details. They're basically abstract notions of sets with some operations defined on them, like sorry, excuse me, like unions with properties like closure and associativity with the what do you say, an identity element. So some of the properties, if they satisfy, then we say it's a group, right? So like that, we can make a group of things like remainders. So we first choose a divisor, say suppose B, and then we look at the set of all possible remainders when things get divided by B. You can get 0, you can get 1, you can get 2, up all the way up till B minus 1. Right. So this here is called the residue class modulo.
Sir, it is the set of number with which B is divisible.
No, this is the set of remainders which you get once you divide any number by B. So this is the, let's not abuse this notation, set of remainders when any natural number is divided by B. So this is the residue class modulo B. So why such fancy names? Okay, since so what is what is a relation? What is a relation? Like mathematically, we
So
by
relation
relation.
is the number of is a subset of the Cartesian product of two sets.
Yeah. So nice. That was nice. So suppose you have a set A, right? A set of numbers, not necessarily numbers. It can be set of anything. Then you pick, when you talk about this set, this crosshair doesn't mean product. So this stands for Cartesian product. So suppose we have uh, A, B, C, D in set A. So A is a finite set. So when you find the Cartesian product between A and itself, you basically club all possible pairs of elements and make up a set of pairs, right? So this basically has 4 times 4 many elements, which are 16 elements, starting with AA, AB, AC up till AD. Sorry. And also BA, BB.
Sir,
Yeah.
what is the X in the AXA part again? What is the X?
It stands for the Cartesian product, which is the
Oh,
Cartesian
okay.
product between the two sets, which is both A here. Right. So it
Okay,
has
sir.
up till last we have CD, sorry, CACC up to CD, 16 elements. Observe that Cartesian product we consider AB and BA as different elements. So these are ordered pairs. We don't consider them as like same elements. So we consider them differently unless otherwise stated. So a relation is a subset of this Cartesian product set, right? So you take few of the pairs like say suppose A, B, C, D, right? So that is like a different definition of relation. Like you might know that inequality is a kind of relation, right? So how is this symbol even related to this set of pairs, right? So say suppose you have a finite set and you want to define a relation over this set. Say suppose the relation rho. This is the Greek symbol rho, Greek alphabet, sorry, small rho. So you want to say 1 rho 2, that is 1 is related to 2. So this is equivalent to or implies that the pair 1 2 is inside the relation. You have called that relation rho, and the symbol for that relation rho is rho itself. So you can say like rho. So it might be a bit confusing, but here this rho stands for the relation. And this here is just a symbol. It's a symbol which indicates 1 and 2 are related. Now 1 and 2 are related doesn't necessarily mean 2 and 1 are related, right? So this is also ordered, right? Since the corresponding pairs are ordered. So here this less greater than operator, you can treat it as a relation. So what is the set, or what is the set representation of the greater than relation? Well, it has like pairs like 2 1, 3 1, 3 2, and 4 1, 4 2, 4 3. Yeah. So 1 2 3 4 5 6. So you have 6 elements in the greater than relation. That's why you can write 1 greater than 2, since you know 1 2 is inside that relation, inside that set. Sorry, I mean.
Sir, here greater than is equal to rho. Like they two are relation.
Yeah. This is a symbol. You can use greater than. Uh, like greater than is a special relation. We know what it means intuitively, since people didn't define it in terms of subsets of Cartesian product of sets. They just like found a way of having a partial order or a complete order between uh, real numbers, right? Between real numbers. So greater than relation is only defined in the context of real numbers. So it's basically a subset of. Okay, so this is the symbol for subset. Stands for subset. So greater than relation is a subset of R cross R, the Cartesian product between real numbers and real numbers. So set of complex numbers doesn't have a no order, right? So you can't say like 2 plus 5i and 3 plus 4i. So there doesn't exist any notion of magnitude or like which one is larger, which one is smaller. Although you can check for equality, like this is certainly not equal since the real parts and imaginary parts are not equal. Well, people have attempted to define a partial order on the complex numbers. Like partial order is something that doesn't satisfy uh, the transitive property, or yeah, and it also doesn't necessarily have like any two elements in a set may not be related, right? If any two elements in a set are not related, then it's called a partial order. Actually, you can also represent these partial orders or relations in a graph. Like you can say 1, 2, 3, 4, the set that I was originally talking about, are points on a plane, which we can say nodes on a plane. And then they are connected by directed edges. I can say there is an edge between 2 and 1 directed from 1 towards 2, and all these pairs, I can treat them as directed edges. So 3, 1, there is an edge 3, 1, there is an edge 4, 1, there is an edge 3, 2, 4, 2, 4, 3. That's all. 1, 2, 3, 4, 5, 6. There are 6 edges, and this is a directed graph. So all the three representation, the directed graph, that intuitive notion you have of the symbol greater than, and that subset of Cartesian product of the set 1, 2, 3, 4, all of them represent the same relation, the greater than relation, right? So that's how people abstractly come up with different notions to represent the same thing. Just because a change of perspective might lead to interesting problems and even interesting solution many a times. So why was I talking about this relation stuff? Okay, I was talking about residue classes. So residue class modulo B. Okay, so when you say you have like let's take the number 5. So what are the numbers in its residue class? We have 0, we have 1, we have 2, we have 3, we have 4. So only these 5 possible remainders are there in the residue class modulo 5, right? So let's see which numbers give remainder 0 when divided by 5. Right, so they are 5, 10, 15, up to like all the multiples of 5. Then we have 5 plus 1, 6, 10 plus 1, 11, 15 plus 1, 16, and so on. Here also we have 7, so on. Right. So these infinite sequence of numbers, 0, 5, 10, 15, dot, 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 this series we can think of like, you see like any natural number n, take any natural number n, and there will be a column in which you will find that number, right? In this expansion, you can think of this as a column, this as a column, this is a column, this is a column. So we have, you can like write the natural numbers in a infinite cross 5 table. So this is a infinity cross 5 table, as and every natural number is placed in one of the cells. So that's why these numbers, these top numbers 0, 1, 2, 3, 4, can be thought of as column headers or column titles. That's why we call them as residue classes, because they are like a class. They partition the set of natural numbers into 5 disjoint and mutually what do you say? Mutually exhaustive sets. So this is what you called the Z5 class. Well, you write it as Z5 or 5 times Z, or yeah, like we generally include the negative numbers also in this table. You can just do it on the top, like say suppose -1, -2, -3. Sorry. -1, -2, -3, -4, -5, -10, and so on. Yeah, so we are including the integers also, negative numbers also in this categorization. So we can see that 4 is actually congruent to -1 when we talk about modular classes, modular 5, right? Why is this? Because if we add 5 to the number -1, you get 4. So we can say like A is congruent to B mod 5. So this implies there exists some number K inside naturals. We can assume like A is greater than B or something, greater than or equal to B. So there exists, no, not equal to, since we have assumed K is a natural. So there exists a natural number K such that A is equal to B plus K times 5, right? K times 5. And this K is actually unique. Can give the exclamation sign. So that makes 7 congruent to 2 mod 5 and 10 congruent to 0 mod 5. Alternatively, you can write it as 7 is congruent to -3 mod 5 and 10 is congruent to, like it's still 0 mod 5, but you can write something like -5 or even -10. Okay, they are all equivalent. When you look through the glasses of mod 5, they are all equivalent since they lie in the same class. So this class, like there are a few properties of this relation, this equivalence relation. This is also a relation. This says that if we talk about the Cartesian product representation of this relation, then we basically have AB. A is in words you can say A and B give the same remainder when divided by B. So A and B give the same remainder when divided by B. Sorry, by 5. So this is basically the Cartesian product representation of congruence modulo 5. So this relation is not just this symbol. It is actually this along with, okay, so So it's congruence mod 5. Okay. And for any relation, we can like dig up some properties. So here, this congruence relation also has many properties. When you can say things like reflexivity. So when you can say A is congruent to itself modulo anything, like anything, P, any natural number, doesn't need to be a prime. Right? You can say things like if A is congruent to B mod P, so if B is congruent to C mod P, this implies, so both of them imply, since they are connected by a what do you say, logical operator, and so A is congruent to C mod P. So basically says if A is Q1 P plus B and B is Q2 P plus C, so they both imply A is Q1 P plus Q2 P plus C, or Q1 plus Q2 P plus C. So you can take this Q1 plus Q2 as Q3 and write A equals to Q3 P plus C, which proves the claim that A is congruent to C mod P. Since we know when anything is congruent to any other thing, where did I write that relation? Yeah, here. So A is congruent to B mod 5 when A equals to K times 5 plus B. Okay. So these are many properties. They actually have a names. Like this is called reflexivity. This property is called transitivity. Then there is something called closure. Closure means that any natural number is congruent to another natural number modulo 5. So you can't when you take the relations congruence, it doesn't send numbers out of the set of natural numbers. Right? It's closed, and it's complete in the sense. Okay, it's not complete. Congruence is not complete, right? So this is actually an equivalence relation. So what is the equivalence relation? Equivalence relation. Equivalence relation is a relation that partitions the parent set, like set A, suppose, which we were talking about a few moments ago, right? Yeah, on which the relation is defined into many disjoint union of many sets, like A1, A2, A3, A4, A5, and A6. Yeah, right. If we talk about the residue class modulo of 6, you get 6 different partitions. You can think of 0, 0, 6, 12. These numbers go into this partition. Sorry, not that. This partition. And there's 1, 7. They go here, and so on. 2, 8. They go there. So basically, they divide the partition the parent set A, which is in this case set of naturals, into disjoint. Uh, disjoint means the set don't have any intersection. So intersection of any two sets, so any two AIs intersection AJ is null set for all I not equal to J. Right. Okay. So if a relation has this property, then this is called an equivalence relation, and congruence has this property. So congruence modulo P for all P in N is an equivalence relation on Z, the set of integers. Just a minute.
Can you please explain this once more?
Which one? This equivalence relation, right?
Yes, sir. Yes.
Yeah, so first we talked about what is a relation. And as one of you pointed out cleverly, that a relation is a subset of the Cartesian product. So what is a Cartesian product? Cartesian product is generally a set which has pairs of elements of the parent set. So here this Cartesian product between A with itself has pairs of elements from A's, like both A and B are from A. So the Cartesian product has all possible pairs. If we take a subset of that, that is, if you remove few of the pairs, then you get a relation, basically. And as we have seen, a relation can be represented in many ways, with a directed graph, with like some notion of magnitude, like we do it in less than or equal to sign. And here this congruence relation, this is another notion of relation which we are defining from the lines of divisibility. We can say A is related to B, or A is congruent to B modulo some number P, when A and B both give the same remainder when divided by P. So that's why I formally defined it as this. So A and B are two numbers. If they are congruent, they are only congruent when they give the same remainder when divided by 5. Here, 5 is like 5 can be anything. It can be any natural number. So relation in general can be categorized as equivalence relation when we have when the parent set, like on which the relation is acting on, like the natural number set or the integers, when when that parent set is partitioned into many disjoint sets, into many disjoint parts, like that first column, second column, third column, fourth column, fifth column, all these columns, no, none of the numbers are common, right? So the first column, none of the numbers which appear in the first column will appear in the second, third, or fourth columns. So all the columns contain distinct numbers, and all of the columns in total contain all the numbers that can appear in the set of natural numbers. So we can say that natural number is partitioned into disjoint parts by that congruence modulo phi relation. So that's what I have pictorially represented here abstractly as A1, A2, A3, A5, A4, A6. So this is the abstract representation of congruence modulo 6 representation, right? So here we are dividing by the number 6. And here these are the remainders. This is the 0 remainder, this is the 1 remainder set, this is the 2 remainder set, 3 remainder set, 4 remainder set, and 5 remainder set. Uh, is this somewhat clear?
Yes, sir, understood.
We can actually further say, so we can further say that if a relation magically satisfies these three conditions, then it's always an equivalence relation. So what are these three conditions? The first one is reflexivity. Second one is symmetric. Sorry, spelled it wrong. And transitivity. I have already mentioned two of them previously, so let me recall. If A is related to B, I'm using the row operator as a generic notation for relation. It can be greater than, it can be less than, it can be congruence, it can be anything. So A is related to B and, sorry, not B. A is related to A. This implies or this implies the relation is reflexive. So whenever any element is related to itself in a relation for all A, so for all A in that parent set, capital A, so that implies that relation rho is reflexive and symmetric. What does it say? So A is related to B. This implies B is related to A for all AB in A. So that means the relation rho is symmetric, since like there is a symmetric property, like the position doesn't matter. If the pair AB is in that set, that Cartesian product representation of rho, then so is BA, right? Like this congruence is symmetric, since A is congruent to B, means A and B give the same remainder when divided by P, which simply means B is also congruent to A. So it's not uh, position dependent. Oh, okay. Is my voice too low or something? I'm using a headphone. I don't think. Okay, I will try to speak louder, Pritish. Okay.
So that means A and B are equal.
Which one?
So symmetry.
Yeah, symmetric means A and B are related. Like A and B are related and B and A are related at the same time. Then the relation is symmetric. Like if
Sir,
you,
A
yeah.
point A comma B and B comma A is only equal when A and B are equal.
No. These are not points. Sorry. These are like when if you think like this is the Cartesian coordinates of a number or something. These are just pairs of numbers. They don't inherently represent anything. They're we give them meaning. Like here in this context, we have given them the meaning that A is congruent to B modulo some divisive, like say suppose P. Okay. So we say like A is congruent to B. This is equivalent to saying A and B is in some kind of a set, which abstractly represents this congruence relation. So this is in the set of what can we say? Yeah, that's it. That's that I'm representing as this double quotes the congruence modulo P set. Okay. Like for 5, like suppose A is this set 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have the relation congruence modulo 5. Okay. I'm writing it like this. Is not standard notation. It's just what I'm making up right now. So this set is a set of pairs of things that are related. Not five. Let me do it for three. Three will look much better. So here we have 1 and 4 and just 1 and 4 in one as one pair. Then we have 2 8 as another pair. 3 9 as another pair. 3 6 as another pair. 6 9 as another pair. So you get how I'm constructing the pairs since they have same remainders. I am just picking randomly two numbers and check if they have the same remainders. Then I'm placing the corresponding pairs into the relation. So not only we have 1 4, we also have 4 1, we also have 8 2, we also have 9 3, 6 3.
So 6 comma 9, the remainder will be 2 comma 3.
No, I'm dividing by 3 as I just mentioned. So both the
Yes, sir.
remainders are
Then
0.
6 comma 9 will be 2 comma 3.
No, I'm talking about the remainders, not the quotients.
Oh,
Right.
okay.
Yeah, you got it right. And also there will be things like 1 1, 2 2, 3 3. That's what makes this relation reflexive. Like the numbers itself are related. Since obviously you can say that if you don't, like, what is the remainder when you divide 2 by 3? You get 2, right? Same is the case for 1. When you divide 3 by 3, you get 0. Or suppose you don't, like, you can say 0 is equivalent to 3 since both of them have the same remainder. Right. So 9, 9.
Sir, but why are we only taking it in pairs, sir? We can also take it in like triples or like quadruples.
Yeah, that's because a relation is defined as a subset of the Cartesian product. And the Cartesian product only has pairs, not tuples or quadruples. So if we want to call it a relation by any means, we have to make it a subset of the Cartesian product. And
Okay.
Cartesian product is A cross A, that is the set which contains all possible pairs. It has like so how many pairs can A cross A have? So let's think about it. So each of the pairs have two places, like the first one, comma the second one. The first one can be filled in 1 and 1, 2, 3, 4, 5, 6 up to 9 ways, right? So 9 times 9. So there are 9 possible ways to pick up a pair from the set A. So all those pairs are in the Cartesian product between A with itself. So we are only available with that 81 pairs, right? We can only pick some of them and discard the rest. That's how I should get any relation which is defined on the set A. That's and one of that subset I'm calling it as R under R subscript congruence modulo 3. And that relation is exactly defined as this subset 1, 4, 2, 8, 3, 9, all those pairs where A and B give the same remainder mod 3 or give the same remainder when divided by 3. Right. Any doubts?
Sir, I didn't understand the last part.
Like why it's not a tuple or quadruple and a pair? That part.
Yes.
Uh, it's just a formal definition. Like you can talk about things like A cross A cross A. That's the space of all tuples. Uh, like all tuples with elements from A. You can say like 2, 3, 4. Like it has all possible tuples. Each of them are from A. So there are 9 times 9 times 9 or 729 many things in the triple Cartesian product of A. This is also sometimes represented as A cube. Right. That's why sometimes in problems you must have seen things written like consider points in R3, consider points in R2, consider points in Rn. These are like the Cartesian product between real numbers. You can think of, like, when you think of a coordinate x comma y, you can think of x as something in as a real number, and y is another real number, right? So what is x comma y? It's an element in the Cartesian product of R with itself. That is the set of all possible pairs of real numbers. So this pair xy, which can be which actually abstractly represents a point on some planar lamina or something. It's mathematically represented as a pair of real numbers, which is a element uh, of the Cartesian product between R and R with itself. And similarly, we can think of any point in 3D as xyz, where xyz, each of them are real numbers. So the point or the tuple is an R cube, or R cross R cross R. Right. And you can like go on, like you can say like all the set of all quadruples x, y, z, w in R4 in four-dimensional space, while the fourth dimension might be anything like magnitude of electric field or electric potential or anything. And then most probably people define it in a different way, not as coordinates, but as mappings from three-dimensional space to real line. This is like in a function. I will later formally define what is a function. For now on, sorry. But you might have also seen these used interchangeably as Euclidean spaces. So
Yes, this one is like more heard of.
yeah, Euclidean spaces. So why are they called Euclidean spaces and not simply Cartesian product of real numbers? That's because whenever we talk about Cartesian product, it's just a set of tuples or pairs of quadruples. Like it's just a set, nothing like all those elements or all those tuples, they don't have any relation between them. But a Euclidean space is a special kind of a set of tuples or set of pairs which have relationship between those tuples. Like there are only fixed rules with which you can add those tuples, multiply them, multiply or find dot products and cross products, take norms, or there is notion of distance in those spaces. Similarly, there is also a notion of scalability, like you can scale a tuple by another real constant. All those come into in the realm of linear algebra and field theory. Like they actually form vector fields. Like those tuples are like linear algebra. Like mathematicians who study linear algebra call these tuples as vectors. So a vector is abstractly represented as x curl or x with the arrow on the top is inside some vector field v, which is defined on an uh, underlying field. This R, yeah, like people have a concept of fields. So what is a field? Well, I just talked about like there are things. Okay, yeah, not there. Yeah, here. So I just said like groups, like this residue class modulo B. This is a group. Like why is it a group? Like there are a group has finite number of things. Like finite groups have finite number of things. So there is 1, 0, 2, all these things in a set. So this is a set. Along with you have some operations like you can. Okay, I haven't defined those operations yet, unfortunately. Okay, so let's not get distracted and first let's define the operations in congruence. So So what are the operations that we can have with these congruent classes like A? So we can say A is congruent if we have A is congruent to B mod n, like 5 is congruent to 2 mod 3. That is, we get remainder 2 when 5 is divided by 3. And we also know like 7 is congruent to 1 mod 3. So we can add them up, like 5 plus 7 is 12 is congruent to 3 mod 3. You see, it's true, like 3 divides 12, right? So we get 0, and 0 is actually in the same residue class as 3. This is also the same residue class as 12. So 3, 12, 0, they're all congruent when we look through the glasses of 3. So this property holds that if A is congruent to B and C is congruent to D mod n, then this implies C plus A is congruent to B plus D mod n. Don't have space. Yeah. This is the first property. It's property number 1. Property number 2, we have A congruent to B. Then we can actually multiply it with some constant C. So C times A is congruent to C times B mod n. So let's see when can we do that. It's not actually free of any constraints. There are constraints on C which we have to look for. Let's discover it. So let's say we have 5 congruent to 2 mod 3. And I want to divide both sides, multiply both sides by 7. Yeah, right. Can I do that? 7 times 5 is 35. I want to say it's congruent to 7 times 2. That's 14. So what's the remainder when we divide 35 by 3? You get 2, right? And what's the remainder when we divide 14 by 3? You also get 2. So in this case, they're equal. Sorry.
Yeah, sir, what is the symbol above congruent sign?
This one, right? This is a question mark. Like whenever I want to say like, is A equal to B, I will put a question mark over that equality. So whenever I say, is A congruent to B mod n, then I will write it as A with a question mark over the congruent sign and like that. Is that okay?
Yes, sir.
Okay. Okay, so let's try with a different modulo. So let's take modulo 4. 7 is congruent to -1 or 3 modulo 4. Why is it so far away? And suppose I want to multiply it with 2. So 2 7s are 14. So 2 7s are 14. And we want to find if it's congruent to twice of 3, that's 6. So 14, if we divide by 4, we get 2. And 6, if we divide by 4, we also get 2. Right. So that just makes you feel like it always happens, right? Then it must be like, then this is true. So it happens for all C in N without any restrictions. So we just discovered a property. Like whenever we have things on both sides of a congruence expression, you can multiply them. You can multiply both sides with any constant, like any C. even with 0. Right. The third property that we have is subtraction. So I added things. Subtraction should also hold. So A congruent B mod 4, not 4, not mod n, and C congruent D mod n. So suppose we have both these expressions. So what do they imply? They imply A minus B is congruent, sorry, not B. A minus C is congruent to B minus D mod n. How is it true? Let's check with the example. 5 is congruent to 2 mod 3. 7 is congruent to 1 mod 3. Okay. That will run into negative numbers. So let's make it 11 instead. So 11 is congruent to 2 mod 3, right? And 7 is congruent to 1 mod 3. From that we can say 11 minus 7 equals to 4. And is it congruent to 2 minus 1 equals to 1? Yeah, since 4 gives the remainder 1 when divided by 3. Right. So this is true. And you can check for yourself with other numbers. This always holds. And the last property that we have is of, no, not the last. Yeah. So division. What about division? If you want to divide A by some number D and B by that same number, does the sign of equal congruence still hold? Here you will have some real constraints on D. So let's, yeah. So 7 is congruent to 3 mod 4. These are co-primes, right? Okay, let me cook up an example. So 6. So 6 is congruent to 2 mod 4, right? What if I divide both sides by 2? 6 by 2 is 3 and 2 by 2 is 1. So that means 3 is congruent to 4 mod 3. Sorry, 1 mod 4. Is that true? Like, what is the remainder when you divide 3 by 4? The remainder is 3, right? So what are the numbers in the corresponding residue class of 3? They are 3 and 4 plus 3 is 7 and 7 plus 3 is 10. Sorry, not 7 plus 3. 7 plus 4 is 11. 11 plus 4 is 15 and so on. So this is the residue class of 3. And what is residue class of 1? It is 1, then 5, and 5 plus 4 is 9, 9 plus 4 is 13, and so on. So they are not equal. Like they are different congruent classes modulo 4. So this congruence doesn't hold. So that means we can't divide by a number 2. Like then this doesn't hold. It turns out like this sometimes hold. Like if we take modulo 4, sorry, not 4. Yeah, let's talk about this example. So, yeah, so 9. So 9 is congruent to, this here doesn't do that. Okay. Okay, we have to change the modulo for that. Like 4 is just too small a number with just one prime factor 2, right? So can't do interesting things with this. Basically, the theorem says that if you want to divide by some d, So if A is congruent to B modulo n, then A by D is congruent to B by G modulo n if and only if the GCD. So sometimes we write GCD without the word GCD. So GCD of n and d is 1. So this here stands for GCD of n and d. And GCD stands for greatest common divisor. So what is greatest common divisor? Well, it is what it says. It's the greatest common divisor. So what is a divisor? Yeah. So what is a divisor? So as I told you that the fundamental theorem of arithmetics is any number, n for that matter, can be factorized into prime numbers, into product of powers of prime numbers. So p1 power alpha I times p2 power alpha 2 up to pk power alpha k. Right. So when I say greatest common divisor, so you can say what is the divisor of n? So you can say p1 is a divisor. You can say p2 is a divisor since both of them divide n. So p1 divides n and p2 divides n. Right. So this symbol, this pipeline operator, as I previously introduced, stands for divides. So p1 divides n. This implies n equals to p1 times q plus 0. This is the division algorithm, which says there exist unique q and r. Here r is 0 and q is a natural number. Right. Similarly for p2, p2 is like n equals to p2 q2 plus 0. So yeah, so both n p1 and p2 are divisors of n or factors of n. So what is the difference between factors and divisors? Anyone? Any wild guesses? What's the difference between factors and divisors? So I'm posing the question to the whole class. What's the difference?
Factors are special numbers which will leave a remainder 0 when it divides the number.
And what are divisors?
They can leave any remainder, sir.
No, they also leave remainder 0. Like if you Google up those, okay, let me just try Googling them. So Splashlearn says a divisor is any number that divides another number. A factor, however, is a divisor that divides the number entirely and leaves no remainder. Pretty circular definition. Let's see what Stack Exchange says. They are using Wolfram hyperlinks for linking to the definitions. So
Sir, I think divisor is a number with which, when it is divided, it can leave any remainder, but factors will only give 0.
uh, that's actually a wrong definition. If you check any book on number theory, like okay, I have not talked about any books yet, so these are few books that standards in this literature, and you can like look into one of them or buy a few of them. There are PDFs also available freely in Z Library and LibGel and all that. So first one is excursion in mathematics. So an excursion in mathematics. This is by four authors: M.R. Modak, V.V. Acharya, S.A. Khatre, and V.M. Sholapurkar. Yeah, Sholapurkar. So this is the most commonly used book in RSM. Next we have Elementary Number Theory by David M. Burton. So, elementary Number Theory by David M. Burton. There's also this funny book named, there are many books actually. This one is called The First Steps in Number Theory, a primer for divisibility by Sailesh Shirali. I like when I was young, my father got me this book in class 6 or 7, I suppose, and I was pretty interested. So this is not generally followed in RSM, by the way. It's a pretty basic book. Plays with numbers and all that with divisibility and GCD. So a primer on divisibility by Sailesh Shirali. There are other books too, like there's the pre-college maths, which almost has everything in required in Olympiad or ISI and CMI, like from number theory to complex numbers to polynomials, sequences, series, and everything. And there is a very advanced book too, which is sometimes also referred to as the Bible of Number Theory, and that's the Theory of Numbers by G.H. Hardy and Wright. Right. So G.H. Hardy, he's a famous number theorist. He's a 19th century number theorist, by the way. He's already dead. So the name of the book is Theory of Numbers. So there used to be a time in England when, like, whenever anything happened in Europe, like any new discoveries or any new theorems come over, they were done either by, like, people used to say either Hardy did something or Littlewood did something, or Hardy Littlewood both made up this result. Like there were only two prominent scientists, prominent number theorists in London at that time, Hardy and Littlewood. Right. He's pretty famous, G.H. Hardy. There are other famous scientists too, like Fermat. He's actually a French mathematician. His name is pronounced as Fermat, and Gauss, Carl Friedrich Gauss, and Euler. I guess his full name is Leonard something Euler, right? And there's like Mercedes and who else? Wilson. Right. Uh, as we go on, we will see there are lots of theorems and results named in these scientists, right? Okay, so what's the difference between factors and divisors? Oh, my Apple Pencil is running out of battery. Sorry, then I have to stop writing for a few minutes. As of it, only 10 minutes are remaining for this class. So for those 10 minutes, uh, let's see what we can discuss. So factors and devices, I don't think like they have any difference or anything. Like both of them are same thing. Factors are numbers which divide a given number with the remainder zero, and devices are also like numbers which like when used generally are also same to as factors. They divide without any remainders. Like you say 3 is a divisor of 6, but you don't say 3 is a divisor of 7 because you don't like you get a remainder of 1, right? So whenever I will use divisor, the term divisor in my lecture notes or anything, I will mean factors. Okay, let me be clear about that. And so greatest common divisor or the greatest common factor, as you might say, GCF, is the like. So how do you get the greatest common factor of n and d? So you have to find a number which divides both n and d, and any number which is greater than that number won't divide n and d. So it's the greatest number or the greatest divisor or greatest factor which divides both of them. And how do you mechanically find that out? Well, you must have learned many methods to find HCF or GCF or GCD when you were in your elementary school. Like there is a factorization method. You factor explicitly those two numbers or three numbers or four numbers which you are given to find the HCF, and then you do like uh, okay, let me illustrate that method. So you have suppose 12 and 18. So you want to find the GCF or GCD or 18 and 12, also known as HCF of 12 and 18, highest common factor. So you first prime factorize 12, so it's 2 times 3, 2 to the power 2 times 3, and 18 is, I guess, 2 times 3 to the power 2, right? So what do you say? What is a GCD? So GCD is 2, and then you take the minimum of the two powers, 1 and 2, times 3, and then you also take the minimums of the two powers, 1 and 2. So you get 2 times 6, 2 times 3, that is 6. So 6 is the GCD of 12 and 18. So GCD of 12 and 18. There's also a long division method, as far as I remember. Suppose I guess in that what you do, you divide it. Okay, so you divide it. So it's 12 ones are 12. So it's 6. It leaves a remainder 6. Then you again divide 12 by that remainder. You get 2. So as soon as you get 0 remainder, or it is perfect, it divides the number perfectly. Then you declare the corresponding divisor as the required HCF. Right. So this method, as we will see further see that this is known as the Euclid's algorithm. Euclid's algorithm. This Euclid is like a ancient Greek mathematician who did a hell lot of things. Like he founded the Euclid's geometry, gave 5 axioms, and everything. And he claimed like all the geometry on plane surfaces follow his 5 axioms, and those are the basics of what is known as Euclidean geometry in the modern mathematics. There also exist things like the non-Euclidean geometry, which mostly violate one of those axioms, and that's how we name them. Like if they violate the 5th axiom, then it's called the forgot what it's called. Basically, the fifth axiom say that two lines are parallel when they don't intersect, and like yeah, and the distance between them is constant and all that. So yeah, so there are surfaces or spheres which mathematicians have constructed abstractly, which have like two parallel lines but they still intersect, or two non-parallel lines but they don't intersect. Yeah, so very weird stuff. That's how Euclid got his name into geometry too. And this Euclid's algorithm, I will discuss it in the next class, also uh, like shows us why this thing works. Uh, Actually, the main role of you like yeah, the root cause of Euclid's algorithm to work is that division algorithm, which says that when you divide any number by another divisor, you always get a unique remainder and a unique quotient if the remainder is strictly less than divisor. So you can keep on dividing the divisor with that, sorry, the remainder with that divisor till you get a zero remainder, and then you can substitute that equation back to the previous one. And if you keep on substituting till you get to the first equation, then you will get a closed form, which is you can write GCD of A and B is equals to some x times A plus some y times B. So you can express the GCD as linear combination of the given numbers A and B. So these A and B are not natural numbers; they are instead integers. They are negative, obviously. Like they can be negative. One of them is negative, one of them is positive. So by substituting and back substituting those expressions or those equalities that we get in the division algorithm, you get an expression of this sort. And then there is another theorem, that is the Bejout's theorem, I guess. I might spell this wrong. Bejout's theorem, which says that any GCD, like for any two numbers, the GCD can always be expressed like this number, ax plus yb. Here, x and y are not unique, but you see, like, whenever you can express the GCD as ax plus yb, right? So basically, okay, I will talk about it in the next class. It's already about to get too late. So, okay, as
So,
an assignment, yeah,
are you
please.
going to send these notes on the group?
I'm actually thinking of making a Google Classroom, and I will keep on updating the notes together with the recordings of this class, which I have recorded in that
Oh,
classroom.
okay.
So
Okay.
I will advise all of you to join that classroom as soon as possible. I will provide the link in the WhatsApp group description.
Sure, sir.
Okay. Okay. Then, as an assignment, uh, I want you to play with this congruence operator, and you can check one of these three books that I just mentioned. Uh, I recommend you to buy this buy the first one, the very first one, An Excursion in Mathematics, by the four Indian authors, since this is mostly the most studied one in RSM, and it also has most of the problems solved, and many years question the previous year question paper of RMO and INMO, I guess the last 10 years, right? Yeah. So if any of you are interested or have aspirations for appearing in the Olympiads, then probably you will also already be familiar with these two exams. These are the regional level exams or preliminaries before you take part in the International Olympiad or IMO. Okay. And the next thing that you can do is try to solve if you get time, I mean, if you get time to read all the sections from page number skip the first page, which talks about well ordering principle, mathematical induction, and strong form. Skip that first page. Read theorem 2, the division algorithm, and you can skip Béjou's theorem for now. There are things about Euclid's algorithm you can have a look and at the proof too.
Which book, sir?
This one, the first one, an excursion in mathematics.
Oh, okay.
Yeah, this one.
Excursion. Fine.
There's also an interesting proof of why there are infinitely many primes. I will discuss it in the next class, but you can have a look. And then you can try to solve one or two problems from exercise set 1.1. Nothing more. And you can revise this algorithm, this how to find the HCF, this Euclid's algorithm, and all. And you can Google up things related to Euclidean spaces and like fields and vector fields and all that, but they are not necessarily in like right now we aren't bothered about those things since they will come up further way in, I guess, in complex numbers and analysis or calculus. Okay, not now. Okay, nice to meet you. Thank you. We will see
Thank you,
you
sir.
next class.
Bye, sir.
Yeah.
Okay,
Bye.
thank you, sir. Good night.
Good night. Good night. Meet you next week. Thank you.